Yeah.
All right. Our last speaker of the day is Rolf. Before we kick off his talk, though, there's a few things that I forgot to mention about tonight's party. First, it's general admission, so if you have friends who want to attend, they can come and buy a ticket. Second, there's lots of good restaurants and stuff in the reasonable vicinity of the hotel here and the venue tonight. A lot of them are in this guide. Montreal is an amazing city, so if it's your first time visiting or you're coming back, I encourage you to go and explore. It's really nice. So Rolf has been with us many, many times over the last few years, including keynoting in 2012, and has done a lot of trainings over the last years. I'll leave it to you.
Thank you. Hello, everybody. Thanks for coming to my talk. One thing before I begin, when I submitted this talk, I put in for a half an hour, and then as I continued to work on it, I realized it might go a little longer than that, so I requested the last slot of the day so I wouldn't step on anybody else's time slot. It's looking like it's going to be more like a full-length presentation, so if you had plans contingent upon this ending early, I'm not offended if you have to leave early. So I was practicing statically reverse engineering some C++ binaries in preparation for a training class I had planned to offer on the subject. And I figured rather than just using the same techniques that I've been using for 15 years, that I would try to explore. What's up? Okay. Is this better? Is this better? What? Better? Testing? Testing? Is that good?
That sounds good.
Okay.
I'm sorry, it's just because it's picking the sound like this.
Is that better? Okay. So anyway, rather than using the same techniques I'd been using for 15 years, I decided to try to do things differently. I gave myself 2 days for every idea that I came up with to see if it was going to bear fruit or be useful or not. And if it sucked, I just moved on. And for anything that was good, I gave myself more time with it. So I noticed that the vast majority of my time was spent on type-related activities, creating structures, applying types, so on. So that's what I focus on in my automation, and some of the better ideas are relayed in here. So these are automated techniques based on dynamic analysis for type analysis that we then feed back into IDA to enable static analysis. Both of these things are based on DLL injection. So type information is about 75% of what you need to use hex-rays properly. It's utterly crucial. It's the difference between this nasty gibberish here with all these pointer additions and cast dereferences and so on. This is borderline useless, honestly. I don't know if you can even call this decompilation, really. It's more like syntax translation. However, with the type information applied, now it starts to look probably what the original code looked like, minus the names and comments. So this is what type information will do to you, but it's tedious to create and apply this information, so let's automate it as much as possible. So we're going to try to figure out all of the dynamically allocated structures, what their sizes are, where they're allocated, where the fields are located, what the types of the fields are. Every location in the binary that accesses structures relationships between structures, nested structures, inheritance, containments, and function argument and local variable information. And these experiments worked out very well. After the first 2 days, I realized I had applied more type information to my binary in those 2 days than I had done in 6 weeks of manually reverse engineering my target. So after that, I just basically stopped reading code and started focusing entirely on automation. Recovered several hundred structures, tens of thousands of structure references applied to the binary, and so on. So there are 2 main approaches covered in this talk, both of them based on DLL injection. The first one was inspired by some academic papers I'd read years earlier about automated data type recovery. The 2 papers listed on the slide here. However, I am not very expert with DBI-based techniques, so I figured there would be a learning curve to try to start working in that direction. That and having looked at some of the source code for some of this stuff, it was clear that the DBI-based approaches have some fundamental performance limitations. So I wanted to do things my own way, explore related ideas in the same vein, see if I could come up with something a little different, maybe better in some ways, maybe not better in some ways. There's a lot of text on this slide, but I'm going to go over the steps on the subsequent slides. In brief, these tools hook the memory allocation routines in order to record every pointer that gets allocated, as well as the size of the pointer and where it was allocated. And then they run the program under dynamic binary instrumentation, instrument every memory reference, and check to see whether it lies within an allocation. If so, they log metadata about it. And after all that, they post-process the data to rebuild structures or do whatever it was that the thrust of their paper was. So the first step is locate the allocators within the process address space or the binary. These might be function pointers, they might be functions contained within your binary, something along these lines. And then we hook them and divert them into our own routines. The hooks themselves are very simple. As you can see, for example, the malloc hook just passes the request on to the original allocator, remembers information about the allocation, and then just returns the pointer. And the free hook just discards the information about that pointer, calls the original free function. So very simple hooks here and work transparently to the original application. So for each allocation, until it's freed, we're going to record the pointer, the size, and the site where it was allocated. We're going to store this stuff in a binary tree of some sort. AVL tree works the best here due to the height balancing. Red-black trees work too, like STL maps are usually based on red-black trees. Hash tables don't work well here. We need the data to be sorted so we can do lookups. So the malloc hook just stores information in this table, and the free hook just removes information from the table. All right, so now on to the DBI part. So at this point, with the memory allocators hooked, now we load the program under dynamic binary instrumentation, and the goal here is to exercise as much code as possible. So provide whatever inputs you need to cause that to happen, and log the memory accesses. So the instrumentation itself is just applied at every memory access. And simply, we insert instrumentation to look at the destination of the read or the write, see if it's within some existing allocation. If so, log it. For example, this memory reference here will log where it was allocated from, how big it is, where the instruction is, size of the access, the offset into the allocation, and whether it's a read or write. So just run the program under DBI, collect all that information, and you wind up with this gigantic table of data that you collect along the way. First, we segregate the data by allocation site. So just look at where it was allocated and collect all of those records up together. If we happen to know at this point that two sites allocate the same type, then we can just go ahead and merge their information together. And then just take that data, sort them, remove the duplicates, and pretty much you immediately have something resembling a structure. Not a whole lot of type information, but you have the sizes of all of the observed accesses within the structure anyway. A brief digression at this point is that you can also discover contained object relationships from this data, not just recover a flat list of fields, but for example, looking at this instruction, you can see that the displacement is 8, whereas the recorded offset into the allocation is 28 hexadecimal. So in order for that to be true, what must have been true at runtime was that EAX was pointing 20 hex into the allocation. So that means that the program is passing around pointers 20 hex into the structure, which either means there's a contained structure at that location or perhaps just a plain old data type. I have some heuristics to differentiate them. So this information can tell us where sub-objects are, and we can use that to rebuild not just flat lists, but nested data. And as it happens, the data has some ambiguity in it. Some of this comes from just ordinary things in the source code. Some of it comes from compiler optimizations. So I'll summarize them. So this structure has a 32-bit integer at 10 hexadecimal into it, and we can see it's perfectly legal for us to take this 32-bit value and assign it to a 16-bit type or an 8-bit type. So just an implicit cast is taking place here. And as a result, we'll see 16-bit accesses to that field as well as 8-bit accesses to that field, despite the fact it's a 32-bit field. So my heuristic solution to this is just choose the size that occurs most frequently, and it works well. Other ambiguity comes from compiler optimizations. For example, here we're testing a 32-bit flag against a constant value that happens to fit into an 8-bit value. So the peephole optimizer can replace the 32-bit version of the instruction, which is 6 bytes, with an 8-bit version of the instruction, which is 3 bytes. Again, this produces ambiguities on the size, as the field itself is actually 32 bits, whereas the access we see is 8 bits. Same solution as before, just choose the most frequently occurring size. It works well. Related bulk copies such as memset or memcopy, where we might access the data, say 8 bytes at a time, obliviously to what the sizes of the actual fields are, and it's perfectly legal for the compiler to do this. Once again, just choose the most frequently occurring size for a given offset. A messier source of ambiguity is unions, where there are legitimately different objects of different sizes potentially occupying the same memory location. So it's perfectly legal to see both 32-bit and 64-bit accesses to a particular location, for example. So I didn't bother trying to come up with a fancy solution to this. I just used the same one as before. It's not even really a solution. It doesn't work very well, but so be it. We're producing information for the analyst to modify after all. And I just totally punted on array accesses. If the access is non-constant, then just throw it away. So anyway, I just described basically how the DBI-based implementations of these idea works, and it has a few advantages. It's comprehensive, it's fully automated. Pretty much you just identify the memory allocator and press go, and the thing churns away. But it's a pretty heavyweight analysis because you have to instrument every memory reference, and the map lookups get pretty expensive the more allocations happen. So this overhead sort of prevents you from interacting with the application, and this in turn impedes code coverage. And furthermore, it seems like this is fundamental to the approach, and no matter how you try to optimize it, fundamentally that's the heart of the DBI-based approach, is instrumenting every memory reference and comparing it against a map. So I wanted to know if I could eliminate the instrumentation of every memory reference. Also, I wanted to know if I could maybe reduce the complexity of these allocation lookups. The authors chose well-suited data types, but nevertheless, the accesses just get slow by virtue of the size of the data. So I wanted to know if I could reduce the overhead, maybe by reducing the amount of data in the maps, for example, rather than tracking every allocation, maybe allow the user to choose a subset of the allocations that they wanted. And finally, the DBI approaches are sort of these monolithic black box, take binary as input, produce data structures as output, but as a professional reverse engineer, maybe I would benefit from more interactivity with the output. Maybe write GUIs inside of hex-rays, have automation for common type annotation tasks, and so on. So I explored some of these directions in my research, which is replacing the DBI instrumentation mechanism, allowing targeting of a subset of allocation sites. I explored the use of custom memory allocators and tried to make good use of the data that came out. So in thinking of ways to try to replace the instrumentation from DBI, the first idea that came to mind, which is not a good idea and doesn't work, but just use the x86 hardware breakpoints to set memory rewrite breakpoints on the memory that comes back from the allocator. So this has a nice property that there's no overhead. You only incur overhead on the accesses to the memory. Everything else runs at native speed. But on the other hand, you only get 20 hexadecimal bytes worth of breakpoints, so it's kind of fundamentally a non-starter. Then I remembered the BPR command from the soft ice kernel debugger, which allows you to set as many memory breakpoints as you want and of whatever size that you want. It's not only soft ice that implemented this. Actually, IDA has this in large memory breakpoints, and OllyDebug also has this for page breakpoints. So very briefly, this is based upon demand paging on x86, where the process thinks it has a large address space, but really it only consumes physical memory for pages that are mapped. And so the page table entries just define these translations from virtual addresses to physical addresses. The operating system can grow the page tables on demand by adding more mappings. And once the operating system starts running out of physical memory, it goes around reclaiming memory from the processes. This is facilitated by a bit in the page table entries, the present flag. So the operating system will reclaim some virtual memory, set the page table entry to non-present, and then write the contents of the page to disk, and now it has more memory to work with. And later on, once the present bit has been set to false, that if you try to access that page, it generates a page fault. So once the operating system detects a page fault to a page that was written out by demand paging, then it transparently pulls the data back in off the disk, allocates a page for it, updates the mapping and the page table entries, and then resumes execution. All of this happens transparently to the application. So that's the mechanism that soft ice and IDA and OllyDebug are using to implement those memory breakpoints, where you set pages of interest to non-present, then install an exception handler to catch those exceptions, inspect to see whether it was your interesting region that caused the fault, and if so, there's your breakpoint. If not, pass the exception on. So we use this same mechanism to replace the dynamic binary instrumentation. So I'll walk briefly through end to end how this works. So let's just assume that this memory access at EBX plus 4 is something that we marked as non-present. So the processor goes to execute that instruction, but it catches a page fault because the page is not present. So the operating system invokes our exception handler. We then inspect the exception to see whether it was a page fault in something that we had marked non-present deliberately. If not, pass it on to the next exception handler. So if it was, then we log the details of the memory access. So right here, this step precisely is where we're replacing DBI. Once we catch this page fault, we know where, that a memory access took place to some memory that we were interested in. So we can log the destination as well as the source of the instruction. So now we want to let the process continue execution. This can't happen until the page is marked as present, so we do that. But we also don't want these to be one-time breakpoints. We have to regain control of the application after the instruction executes, and then mark the page as non-present again. So for this, we use the x86 trap flag, which is the same mechanism that the debugger uses for single stepping, causes a single step exception to take place after the instruction executes. And then we let the process run again. So the first instruction tries to execute again, and this time it succeeds because the page is present. But then on the next exception, it throws a single step exception, so our exception handler then gains control again. which we check to see, is this the exception we're expecting, a single step immediately after the last instruction that we faulted on for the page fault. And if it is, we continue processing. Otherwise, let the next exception handler handle it. So we just mark the page as non-present so that we'll catch future accesses to that same page, and let the program run again. And so there then is the complete replacement of the DBI-based instrumentation mechanism. Architecturally, I just let each thread have its own thread local ring buffer where it logs these page fault events, and there's a controller thread that's periodically polling all of these things in order to filter them and write them to disk. Basically, the philosophy is just get out of the exception handler as soon as possible, write that data, and get out. Okay, so as for the next direction in this research, I also looked at targeting a subset of the allocation sites. So we just looked at how do we track accesses to memory, but we haven't looked at what it is that we're tracking or how we apply this. So there's two possibilities here. Either we go the DBI route and try to track everything, or we choose certain allocation sites that we're interested in. So if we go the route of monitoring everything, this is very simple to implement. Just in our alloc and free hooks, we have the addition and removal of the memory breakpoints. So on the other hand, the other direction I explored was reducing the amount of data that we were tracking by limiting ourselves to certain allocation sites. So this gives us an opportunity to improve performance. If we're only tracking certain allocations, then it's only going to be certain regions of the heap memory that we're interested in, say the red allocation right in the middle. But since the technique fundamentally works at the page level, it means we're going to take page faults for either of the neighboring allocations or any allocation on the same page. And it gets even worse if it happens that this allocation straddles a page boundary where part of it's on one page and part of it's on the other. That means now we have to track 2 pages for one single object of interest. So we get better performance by only taking page faults on allocations that are interesting to us. So as a result, I decided to allow the user to specify which sites are interesting and then divert them into a custom memory allocator, or at least a separate heap from the ordinary one. And so now our other heap is only going to have the objects that we're interested in. So anytime we get a page fault on that heap, it's going to be something that's interesting to us. So we don't have any uninteresting page faults. It's easiest to just use some off-the-shelf general-purpose memory allocator. I also experimented with using a fixed-size slab allocator. So this is a little more subtle and difficult to apply. Basically, you have to specify a maximum size of an allocation ahead of time, and then every allocation is that size. But on the other hand, the performance really screams. I get about 6.4 million structure accesses per minute using a slab allocator. So in brief, DBI versus DLL injection. Fundamentally, the difference here involves changing the tracking mechanism. Rather than instrumenting every instruction, we target the memory instead. And divert interesting allocations into a custom allocator to reduce the number of page faults that we would take and not be interested in. So I have decided to skip showing off the GUI for IDA and hex-rays. Instead, at the end, I will present a demo of both this and the next one. So I'm going to move ahead. Okay, so now we switch gears. This is fundamentally different. No more page fault type of stuff. This is the second analysis type that I explored in my research. Dynamically tracking the data flow from allocation sites into function arguments. So in brief, the picture is as we see on the slide here, which is here I have some allocation site, and basically I just want to track this data flow. That pointer that comes back from malloc, I want to discover every function that gets called with something derived from that pointer as an argument, and I'm going to record the address of the function, the argument number, where it was allocated, how big it is, and what the offset was. So before applying the idea, first I do some pre-processing, so this part here is x64 specific, where ultimately I'm going to hook every function in the binary of interest, and as it happens, the x64 exception metadata tells you where the beginning of every non-leaf function in the binary is, and also the distance to the end of the initial region. So for each one of these, I'm just going to do some filtering up front, use IDA to figure out is there an invalid instruction here? Is there a control flow instruction like a jump or a return? Is there incoming control flow? So basically what we want to know is, do we have at least 5 bytes at the beginning of the function to hook it by installing a call? So we just go instruction by instruction until we've reached 5 bytes or more into the prologue, and if we haven't failed so far, then we continue to think of the function as a candidate. I also apply some cleanup to the IDB to revert everything to the standardized calling convention of fast call on x64 so that I have consistent labeling of argument locations as integers. So this just involves removing arguments in illegal locations and perhaps rearranging arguments. On this slide, for example, RCX is the first fast call argument and RDX is the second, whereas they're swapped in the prototype here. And then finally, use hex-rays to decompile the function and make a list of every pointer-sized argument. Just record the number and the positions of them. So this is much easier on x64 than it is on x86, where there are custom calling conventions manufactured by interprocedural register allocation, for example. So in summary, we just end up with a table of data, looks like this, where the function is, how many bytes there are in the prologue, how many pointer size arguments, and then a list of the argument positions. So now, on the DLL injection side, so start off the same as before, just hook the memory allocator, alloc and free, and record the same type of information that we were recording in the previous, which is to say every time an allocation takes place, record the pointer, the size, and where it was allocated from. And then upon free, just get rid of this information. So then, for each of the functions that we're tracking information about, I just allocate some new RWX memory, copy over those instructions from the prologue, insert a jump at the end to after those instructions, and keep a hash table of this mapping the original function to this new re-entry thunk that we're going to use to re-enter the function later on. Oops. Then I simply hook every function by inserting a call at the beginning of it to a common logging routine. It starts off as just a little assembly stub that saves the flags and registers and creates a pointer to the stack data and passes that all off to a C logging function. And then on the way out, it's going to overwrite the return address to point it to the re-entry thunk that we just saw on the last slide. Restore the registers and the flags, and return. So on the C side, we just look up the list of interesting arguments for this particular function, and then pass that off to the logging thread. The logging thread just determines to see whether any of these arguments was in fact a pointer to an allocated object or somewhere within an allocated object anyway, and logs. If so, it logs which function, which argument, and then the allocation information. Where was it allocated, what's the size, and what was the observed offset. So in summary, a bunch of data that comes like this, looks like this, comes out the other end. Lots of it, actually. For my target, about 60,000 entries are generated. And that's a good thing. This is very valuable, very useful data. So I decided, instead of going through the slides with the pictures of the GUI, I'll just show you how do you use all this stuff. So this is hex-rays.dll, the IDB. All I've done to this binary is first unmark every library function as a regular function, and then I applied that fast call analysis that I mentioned earlier to correct the calling convention. I have also, in the middle here, so no tricks up my sleeve. I haven't applied any structure references or changed any argument types or anything. You see in the structures window, for example, here's two data structures. So I'll run my script or plugin or whatever. And now load raw structure accesses. And I specified that this corresponded to a known structure. You can also specify unknown structure, in which case it will recover the structure. There we go. So up comes this list of 6,000 collected data entries. So you can right-click and apply structure references to disassembly all, and it's done already. If you refresh, then it shows you it's just applied about 6,000 structure references. And you can see in the structure reference window, for example, where all of a sudden, for example, there's about 1,250 references to this particular structure field. So now for the argument data, first I'll add an allocator, load in the function argument data. That just takes a second. So if you double click that, now you get a list of allocators and what size they allocated. If you double click any one of those, it will show you a list of. That just takes a second. So if you double click that, now you get a list of allocators and what size they allocated. If you double click any one of those, it will show you a list of all the functions where the data flowed into, the function name, as well as the argument number, and some information about whether it was a pointer into an allocation. So at this point, as a reverse engineer, it's your job to figure out which types are being allocated by these sites. I'm not going to do that live in front of you. I have already done that. I will just load those types in for the sites. So going back, now you can see all of the types are listed. So then, for any one of these, now we can apply the types to the arguments that were observed throughout execution. So for this one, for example, so we can look at any one of these, and that presently there's no argument types applied. Whereas if I go back and right-click Apply Argument Types, and then 8 argument types applied across 6 functions. So then if you go back, now both of these things have automatically been changed to the proper type. Right, so another thing you can do with these raw structure accesses is to locate the corresponding variable in hex-rays and then set the type to that data type. So for example, you can see here's your classically hideous looking decompilation with a bunch of pointer plus offset star data basic type dereference. So just right click that one, apply hex-rays types to variables selected. Now I'll bring that one back up. And now it's nice again. We only applied one single variable type, and there's more that we could do, but just that one single type cleans up the decompilation pretty substantially. So in fact, if you were to right-click and press Apply All Types, there would be about 1,750 variables that have types applied to them. It takes a minute, though, because hex-rays has to decompile everything, so I'm not going to do that. And then, in my opinion, the coolest thing that came out of this research was so as you progressively refine your understanding of the types and you create more specific and better type information for some of these sites, that then you can use that information to figure out the types in other structures based on the function argument data that we collected, that we were able to see that offsets from certain allocations and offsets from different allocations were both passed into the same function. So we can use that. If we figure out the type of one, it either directly tells us the type of the other, or at least establishes some relationship. So you can right-click something and say, Show Type Relationships, for example. And then, so these are all of the were both passed into the same function. So we can use that. If we figure out the type of one, it either directly tells us the type of the other or at least establishes some relationship. So you can right-click something and say, show type relationships, for example. And then, so these are all of the types that were passed in to the same argument type from a different allocation. So you can see like, so like there's a vector of integers at 148 and all that. There's one more thing I didn't show off, I guess. I also install a hook inside of Hex-Rays to print this dynamic allocation flow data as an automatic comment in every function's pseudocode to tell you where the arguments came from, what the size was, the offset, etc. So anyway, there's some extensions to these ideas and some challenges in using the information properly. Since we're short on time, I think I'll just skip to the challenges. So as with any dynamic analysis, there's always a question about how do you ensure code coverage. I didn't attempt to approach this problem. Every dynamic analysis has this problem. So the only thing I can offer really is that with the performance optimizations, that you can actually sometimes execute your targets at more or less native speed with no noticeable slowdown. I wanted to show a demo of that, but time constraints presented. There's also ambiguities with what is the type that flows to a particular argument. For example, like if I have this inheritance relationship from the source code, I don't necessarily know that directly from looking at the data that I've collected. So what type should I actually assign for the arguments, for example? And that you can't necessarily just figure this type of stuff out looking directly at the sizes. Like here's an example where we have two derived classes from the common base class, and they're both the same size, and they even both have apparently similar data types, but nevertheless they are different types. So pretty much nesting relationships can cause problems for figuring out types. Not only the inheritance relationships that I just mentioned, but any type of nested structure relationship like what's on the slide here. Like here I have 4 structures nested inside of one another. And then so if I know that there's a pointer at +4 into this structure, well, which type is actually being referenced here? Is that an integer pointer, or is it a pointer to a D type, or a C type, or a B type? Because all of these things begin at the same location. In fact, even if we had the types from the original source code, it's not clear how we would go about answering a question like this. So that's about it. None of the techniques were especially sophisticated, really. On the other hand, though, I think the numbers speak for themselves with the thousands of data types applied and function arguments and just how rapidly it makes structure reconstruction. There are challenges in applying the data, as I just mentioned, but we're especially sophisticated, really. On the other hand, though, I think the numbers speak for themselves with the thousands of data types applied and function arguments and just how rapidly it makes structure reconstruction. There are challenges in applying the data, as I just mentioned, but nevertheless, I've still found these techniques very useful. And I found that my time automating this type of stuff was much more valuable than even reading the code, actually. So this stuff is almost ready. The code's in pretty good shape, but nevertheless, not quite done with it. So I'll release the code sometime next month. I'm giving this talk again at Black Hat, so I will try to have it released before then. It'll be in the standard places it always is: Twitter, reverse engineering, Reddit, etc. So that's it. Any questions?
Hi, I just have two questions. First of all, great tool, looks very useful.
Cool.
Do you have any
Can you
plans
speak up a little bit? Put the microphone a little closer. Thank you.
Sorry about that.
No worries.
Do you have any plans to port this to Ghidra eventually? For the rest of us poor people.
I mean, there's like two parts of this, right? There's collect data, and then the second half is apply data inside of tool. So, you know, the first half of it can be used just directly the way it is. Maybe I will port it to Ghidra. It'll be good exercise, I guess. I don't know much about the Ghidra.
Allocating guard pages in place of what's normally given back by malloc. Alternatively, you could set the page table entry to invalid, and then you'd have to carve out that page from the VOD. But I didn't hear you mention that either. You know, if I'm misunderstanding you or something, please tell me. But how does that actually work?
Call virtual protect with the page present flag not set.
And that raises exception. Okay, gotcha.
And then I use a vectored exception handler to catch what comes back.
Yeah, all right, thanks.
Hi, I have a question. You didn't quite, I think, describe it. How do you map allocations to types? Because you had it in the demo, but I don't think it was mentioned in the slides.
Right. I guess as one of the extensions, I just collect up all of the argument types that I see flowing to the same location, and I try to make clusters of allocations that I think are similar or the same. So from there, I do some investigation, and this is manuals for the most part. Just manually reverse engineer these things, try to figure out, are these things the same type? If they are, then give them a common name and make a note that all of these locations allocate the same thing.
Hi. How do you deal with global structs and stack?
I don't.
Okay. Awesome, thanks. Hi. How do you deal with global structs and stack?
I don't.
Okay. Awesome, thanks.
Hi. Earlier on, when you were talking about multiple different sized accesses to the same fields in the case of casts, and you would heuristically decide to choose the most common size and have that work out for you, why wouldn't you just choose the biggest size? Because I feel like a cast to a larger type would be unusual.
Well, you end up with you know, large sizes due to like bulk copies, like mem copy or a mem set or something like that, which is oblivious to the sizes of the individual fields. So if you chose the biggest field, anytime there was a mem set or a mem copy, you would just obliterate, you would default to the largest size.
This is a good point. I believe you. Thank you.
are you tracking some additional information regarding the types? I mean, if you are, for example, calling like API functions, like open or something like that, you will have like a pointer to handle. Then you can track this information and provide it to your types in IDA. Do you do that, or do you plan to do that?
There is some academic work that does things like that. If you're interested, I could point you to it. A lot of that stuff involves some sort of static analysis, whereas everything I presented here was purely dynamic. So no, I'm not attempting to do anything along the lines of what you just said. I guess, for example, one of the extensions that I didn't mention was you could combine this stuff with static analysis, for example, to figure out references that you didn't directly observe. And so Hex-Rays is able to do stuff like this, like track the data types like you mentioned. So you could combine it with something like that.
I may have missed it. Hello?
Mm-hmm.
I may have missed it, but what do you do with variable allocations?
I'm sorry?
With variable allocations, like it seems you're tracking fixed size allocations and properly defined structures and stuff like that.
So it's not safe to use a slab allocator for variable size allocations like that. So those are your two options, really.
That's not my question. You have a structure with variable size.
Oh, variable size structure. You mean like something with like a character array at the end of it, which might be a variable length or something like that?
Yeah, that will bloat your tracker because you'll think it's unique based on the allocation size, for example.
Well, I do track all of the sizes allocated by a particular site, and you could see in some of this, there's this column here called variable, for example. So if we ever observe the allocation site allocating more than one size, then that flag will be set. But I don't have any really sophisticated answer to that. I thought about maybe writing a script that tries to extract the allocation argument within Hex-Rays or something like this to determine whether it was always a constant number, but haven't done that.
And the last part is in sophisticated programs, the allocation routine is
that. I thought about maybe writing a script that tries to extract the allocation argument within Hex-Rays or something like this to determine whether it was always a constant number, but haven't done that.
And the last part is in sophisticated programs, the allocation routine is wrapped heavily. So at the real significant call site, to reach the actual allocator, you have like, you can't just say return address entrancing.
Yep, that's a good point. So for reverse engineering Hex-Rays, it has its own internal IDA allocator, QAlloc or throw, and also QFree, but it uses a separate allocator for the STL stuff. And so I did run into that exact problem that you mentioned. So I had a conditional compilation. There's target malloc versus target QAlloc, and there's special logic in there for retrieving the return address from the real caller as opposed to the wrapper.
Okay, and just a suggestion, I haven't explored the various DBI libraries, but what about the idea of once you explore a certain function, uninstrumented, and so therefore you progressively discover things, uninstrument, and your performance will increase over time instead of remaining constant all the time?
Is it possible to uninstrument a function?
If it's not, maybe there's a framework, or you can actually add that functionality to that framework, but that's a good optimization technique. Start slow and slowly de-instrument as you go.
Okay. I mean, I haven't explored anything along those lines. Future work, I guess. Anyone else? Oh, it looks like another one. Oh, hey, Julian.
Thanks, Rolf. Good talk. Let's say you want to reverse a linked list, very simple data type. Can you hear me? Sorry. Let's say you want to reverse a linked list. So it's both a recursive data type and also kind of a polymorphic data type. How would you perform in that case? You have like a structure with a next pointer and a void star data.
Yeah. Well, I guess the first analysis that I presented would properly identify like the shape of the fields, like there's a pointer here and there's a pointer here, for example, whereas the type analysis I showed in the second part, based on function argument equality, that would become messier, and it would start to say that all these different types were equal to one another, I guess.
Last one.
Lots of questions.
Thank you. Thank you for your talk. You mentioned your DBI to get all the information needed to reconstruct the structures. What if you can't inject a DLL, or if you want to reverse some part of an unknown kernel or anything like that? Have you tried something along VMI solutions?
I mean, I'm going to guess that if you can't inject a DLL, also DBI is going to be out of the question also. So as for exploring alternative techniques beyond that, no, I haven't.
Thank you.
All right.
Okay,
Thanks, Rolf.
thanks everybody.